Picture this. You step into a space so incredibly vast, you could literally park a fleet of blimps inside. The air is just humming with the vibration of heavy machinery. The sheer scale of the operation makes you feel tiny. This isn't just a factory. It's the birthplace of modern aviation and cutting-edge defense technology. Today, we're taking a documentary-style look inside the hangars of aerospace manufacturing to uncover the environmental footprint hidden behind the creation of these engineering marvels. Welcome to today's Explainer, where we're going to unpack the really rigorous standards used to measure the energy and waste of this massive industry. When you think about a modern commercial jet or an advanced defense vehicle, it's super easy to just picture the final product, right? Soaring through the clouds. But what does it actually take to build one of these things? These manufacturing hubs aren't your standard assembly lines. They function a lot more like small, highly industrialized cities. Building advanced machinery requires incredibly intensive energy systems to power massive operations, and it relies heavily on complex chemical inputs for advanced metallurgy, component manufacturing, and protective coatings. Honestly, tracking the environmental reality of these operations is a monumental task. Okay, let's dive into this. Here is our factory tour itinerary based on SASB standards. First, the aerospace manufacturing footprint. Second, powering massive assembly floors. Third, handling hazardous chemical waste. And finally, auditing the environmental cost.
Let's step onto the floor and kick things off with Section 1, the aerospace manufacturing footprint.
Before we can even begin to understand the environmental impact, we really have to grasp the sheer scope of this industry. The source material outlines that commercial aircraft manufacturers, the folks selling primarily to airlines, pull in about a quarter of the industry's total revenue. But, we aren't just talking about passenger planes here. Defense prime contractors, the ones building fighter jets, space vehicles, naval ships, and missile systems, they make up another whole quarter of the pie. The rest, that belongs to the vast, sprawling network of parts manufacturers. We are talking about a globally distributed industry serving a worldwide customer base with incredibly complex supply chains.
So, with a footprint that massive, how do investors even begin to track the environmental risks? Well, they rely on highly specific SASB metrics to boil all that complexity down to hard data points. Today, we're focusing squarely on the top two categories you see: energy management and hazardous waste management. These are absolutely the critical pressure points for the physical manufacturing process.
And that leads us right into Section 2, powering massive assembly floors. Let's think about what it actually takes to keep the lights on and the machines running in these industrial behemoths. Energy is literally the lifeblood of aerospace manufacturing. The SASB standards mandate that entities report their total energy consumption in a massive unit of scale, gigajoules. Just to put that into perspective for a second, a single gigajoule is roughly the amount of energy a typical American home uses in over a week. Now multiply that by an entire factory complex. The scale is staggering. And this metric isn't just about the electricity bill. It includes everything from purchased electricity to direct fuel usage, and even self-generated heating, cooling, and steam. Plus, when calculating energy from fuels, they don't just guess. The standards require using gross calorific values to ensure the data is as precise as the engineering happening right there on the floor. But it's not just about how much energy is being devoured, it's about where it comes from. The standards require a really clear-cut breakdown. What percentage of this massive energy draw comes from standard grid electricity, and what percentage comes from renewable sources? Aerospace companies are increasingly looking toward a varied mix: geothermal, wind, solar, and hydropower. Even biomass is on the table, provided it's certified to some very strict third-party forestry standards. The type of energy an entity uses heavily influences the reliability of their supply, their cost structure, and for sure their exposure to regulatory risks. Now, here is the really crucial point. In the world of rigorous ESG auditing, an aerospace manufacturer cannot simply claim they use renewable energy just because they bought some green power plant. No way. The SASB standard is exceptionally strict here. To claim renewable energy, the entity must explicitly retain and retire, basically cancel out, renewable energy certificates known as RECs or guarantees of origin. This means the certificate is permanently taken out of circulation on behalf of the entity. If they generate solar power on site but sell the REC to someone else, they absolutely cannot claim that renewable energy for themselves. This prevents double counting and ensures total transparency. Okay, let's pivot and look at the chemical reality in Section 3, handling hazardous chemical waste. Look, you simply cannot build cutting-edge flight technology without generating some seriously intense industrial byproducts.
It's just a reality. Aerospace and defense manufacturing inevitably produces hazardous waste. We are looking at things like heavy metals used in advanced metallurgy, wastewater treatment sludge, and highly regulated solvents required for specialized paints and coatings. Because these materials pose severe environmental and health risks, they're subject to intense regulations governing how they're transported, treated, stored, and eventually disposed of. So facilities are tasked with tracking the total weight of this hazardous waste in metric tons and, importantly, what percentage of it actually gets recycled. But the standards draw a really hard line here that might surprise you. Let's say an entity takes combustible hazardous waste and incinerates it to recover energy, meaning they capture the heat to generate power. Well, under this audit, that strictly cannot be counted as recycled waste. Reused, reclaimed, or remanufactured materials count toward the recycling percentage? Sure. But direct incineration doesn't count. It's a vital distinction for keeping environmental reporting accurate. When you're dealing with massive quantities of hazardous chemicals day in and day out, the risk of a spill is just a constant operational reality. SASB requires entities to track both the number and the aggregate quantity in kilograms of any reportable spills. And a reportable spill isn't just dropping a bucket on the floor. It's defined as any leak, emission, discharge, or disposal of a hazardous substance that crosses the threshold, requiring them to literally notify regulatory authorities. And get this, the tracking isn't limited to a single flagship factory. The scope includes all spills across all jurisdictions in which the entity operates, globally. The rigor doesn't stop there. We also have to look at the aftermath of a spill. The standards want to know exactly how much of that spilled material was actually recovered from the environment, but there is a very strict timeline at play. You can only count quantities recovered through short-term response activities, meaning cleanup that happens in less than 1 year from the time of the spill. And if the chemical evaporated, burned, or dispersed, you cannot claim it was recovered. Any recovery that takes longer than a year falls into long-term site remediation, which involves ongoing stuff like land use controls and site monitoring, and none of that can be bundled into the immediate recovery metrics. Which brings us to our final stop on the tour, Section 4, Auditing the Environmental Cost.
So why go to all this trouble? Why go to such extreme lengths to measure every single gigajoule and kilogram? Well, because these specific accounting codes, RTA 130A1, 150A1, and 150A2, they are the absolute backbone of accountability. They cut right through the corporate marketing jargon and force a completely impartial, data-driven audit of these manufacturing facilities. These codes ensure that an investor comparing the sustainability of one aerospace prime against another is looking at a true apples-to-apples comparison of the physical, environmental reality. The big takeaway here is that these metrics aren't just for show. They are directly tied to a company's financial health and operational resilience. Effectively managing energy consumption and handling hazardous waste, that's not just some regulatory box-checking exercise. Sure, implementing renewable energy systems or advanced recycling takes some serious initial investment. But over the long term, these strategies absolutely reduce an entity's cost structure. More importantly, meticulous management mitigates massive remediation liabilities and helps avoid crippling regulatory penalties. At the end of the day, good environmental auditing is just good business. We've taken a pretty wild tour today. We've looked at the massive footprint of the industry, examined the millions of gigajoules pulsing through assembly floors, and confronted the harsh reality of managing heavy metals and chemical spills. The aerospace and defense industry literally builds a machinery that defines modern human capability, but it definitely leaves a profound mark on the physical world. So I leave you with this final thought. As we continue to engineer the future of flight, pushing faster and further than ever before, can we ensure our auditing frameworks remain rigorous enough to truly weigh the environmental cost of our progress? Thanks for joining me on this explainer, and keep questioning the data behind the design.